Hi, welcome to the second video on proof by induction summations. In this example, we're going to have a look at something more complicated. Before we do that, let's have a little revision of how all of our proof by induction of summations are going to work. So the step one, we're going to do the base case. Step two, we're going to do the assumption. This is pretty much the same for every type of induction. Step three, we do the consideration. This is the consideration step up here. And we're going to employ this little trick. So we split up the sum like this, and then we can replace our assumption. Because remember, our number one goal with an induction problem is to involve the assumption. As soon as we involve the assumption, we're working with something a lot easier than what we previously had. So let's have a look at this example below. At the end of the video, I'm going to show you how to derive this sum. So an alternative proof, we can sort of find it by hand rather than being told it. But like I said before, it's not really a proof technique that we want to learn because it's only going to be applicable to this one example. So let's have a look at how to do this by proof by induction. So first of all, let's have a look at our base case. So base case, n equals 1. So we're dealing with the sum from m equals 1 to 1 of 1 over m times m plus 1. Well, the only term in our sum is 1, so we just put the 1th term, so replacing m with 1, which is just a half. Now, let's have a look at the right side. With the right side, replacing n with 1, we have 1 over 1 plus 1, which is in fact a half. So true for base case. Next, we're going to do our assumption step. So assume true for n equals k, i.e., so we're just stating what this means. The sum from m equals 1 to k of 1 over m times m plus 1 is equal to k over k plus 1. So all we've done is replace k with n in our original expression at the top here. Next comes our consideration step. So we're going to consider the sum up to k plus 1. We're going to do that trick that we always see. So the k plus 1 term, so when I replace m with k plus 1, so 1 over k plus 1 times, well, m, if I replace it with k plus 1, I've also got a plus 1 here, so it's going to be k plus 2 now. Like this, plus, and then I'll sum up to k. So we're just employing that trick that we saw at the top. Next, we can replace that with our assumption. So this is 1 over k plus 1 times k plus 2 plus k over k plus 1. And then it comes to this point and we sort of need a way to target what we're after. So I'm going to write on the side here our target. So our target is what we would expect this to be if instead of we chose n equals k, we chose n equals k plus 1. So we'd expect to have the sum from m equals 1 to k plus 1 of 1 over m times m plus 1 to be equal to, well, on the top we're going to have a k plus 1, and on the bottom we're going to have a k plus 2. So what we're going to try to do is we're going to try merge these two fractions into this. So I've spotted the difference. What we have is two fractions. What we're after is one fraction. So if I can combine them to become one fraction, the rest of the simplification will become a lot easier. So let's have a go. So let's combine them into one fraction. So if I want to do that, I need a common denominator, which means I need a k plus 2 factor on the right side. So I'm going to have 1 over k plus 1 times k plus 2. And to get that k plus 2 factor, I need to times top and bottom by k plus 2. So k times k plus 2. Now, clearly we want to expand because we're after cancelling this k plus 1. So if we expand, we get k squared plus 2k plus 1. And our goal is we want to refactorize. So hopefully there'll be a factor of k plus 1. And we can get rid of that k plus 1 on the bottom. Because that's our main difference now. There's no k plus 1 factor there. So factorizing the top, well, this is actually just k plus 1 squared. Like so. And while cancelling a k plus 1 factor on the top and on the bottom, we get exactly what we're after. So all we've done here is we've kind of done spot the difference. What do we have? What are we after? Well, originally we had 2 fractions, but what we're after is 1 fraction, so we combine them. And then we saw that there's a k plus 1 factor on the bottom, but not in our target, so we needed to get rid of that. The only way we can get rid of them factors is by finding another factor on the top of the fraction. Because then we can just divide by that factor, which is what we found. Hence, we get to this stage. We're not finished though. We need to state our conclusion. So, as true for n equals k plus 1, when true for n equals k, and as true for our base case, n equals 1, it must be true for all n greater or equal to 1 by mathematical induction. So we've shown that our domino effect does in fact occur, and we showed that the starting domino is 1. Okay, there could be a starting domino before 1. It doesn't really work for summations because there'd be no terms in our sum. But the idea is when we're dealing with an induction, we don't necessarily need to prove or find every single case where it works. We just want to prove it for the cases that we care about. So our domino starting at 1, this is all we care about. There could be a domino before that. Maybe we see that in later videos. But the main idea is for what we care about, it starts from 1. Okay, so I said I'd prove this from scratch. I'd find this result. This is going to require a trick called telescoping. So let's have a look at that. So we've got the sum from m equals 1 to n, or 1 over m times m plus 1. Now, whenever you get a sum that's involving a fraction where you've got like a quadratic or a cubic or something on the bottom, you want to first factorize and then split it up. Because what you're going to be able to do is you're going to be able to do something called telescoping, which is what we're going to see. So we're going to apply partial fractions. So this is m equals 1 to n. By partial fractions, this is 1 over m minus 1 over m plus 1. Like this. Now, if I write out all of these terms, we're going to be able to see some cancellations. So when m equals 1, we have 1 over 1 minus 1 over 2 plus, now when m is 2, we have 1 over 2 minus 1 over 3. Now, we're not simplifying because you can see some cancellations. Let's have a look what happens in the next terms. So plus, we're now going to have 1 over 3 minus 1 over 4. So again, this first term is cancelling. Like so. So we kind of see the pattern. This term is going to survive. The first term is always going to cancel with the previous term. So this last term will survive. So if we dot along here like this, we go up to the nth term. So we've got 1 over n minus 1 over n plus 1. Like so. Well, this term is going to cancel. This term would have cancelled earlier. And all that we're going to be left with is 1 over 1 minus 1 over n plus 1. Combining these two, we get n plus 1 minus 1 over n plus 1. just combining two fractions by making their denominator the same, giving us n over n plus 1. I hope that's helpful. I hope that gives you a good idea on how these proof by inductions work, as well as seeing what we call telescoping in action. This comes up in a lot of sort of Olympiad style stuff. It also comes up in the A-level course. If you do that, well, it depends what syllabus you do. But yeah, thanks for watching. In the next video, we'll have a look at matrices, proof by induction on matrices. Very sort of similar style to this, similar trick, same difficulty, maybe a bit harder. But yeah, so I'll see you in the next video. Have a look at the lecture notes and try the practice problem that I've put in there. Maths is a participation sport. You must practice. And if you have any questions, feel free to leave it in the comment section.